Yeah, hi everyone. I'm Debangshu. I'm a fourth-year PhD student at UIUC, and I will be presenting our work on generating Dafny annotations with LLMs. So this is a joint work with Stefan and Olivier, and this was done during my internship at Amazon last summer. So yeah, although I think most of the audience are well aware what Dafny annotations is, but I will give you a brief introductions. Like one of the Dafny annotations is like inductive invariants. You can think of those as hints that help like the Dafny verifier to prove partial correctness of the programs. Like given like the program is terminating, it is correct with respect to the input-output specifications. For example, if you look at the this code, this simple code. So if you just directly try to verify this code with the Dafny verifier, it doesn't go through. But in order to get the proof verified with respect to the input-output specification, you need to add this inductive invariance, which essentially helps like the Dafny verifier to prove the correctness of the programs. Now, the question is who actually provides these annotations. Currently, it is done by like the developer themselves, but as you can see, like the providing these annotations can be quite time consuming, and also it's not that easy. So this is where the LLMs comes into pictures, and we can actually use like the LLM to generate these annotations. So what exactly like the problem we are trying to solve is like given a base program without any annotations, we are trying to generate these annotations that essentially help us prove the LLM to be correct with this input-output specifications. Now there has been already some prior works which try to address these problems, and also there is some benchmarks like DafnyBench which essentially targeted for this problem. Now in this talk, I'll be mostly focusing on like some inference type strategies which essentially helps like improve the LLM performance on this task, and also more importantly, I'll be talking about some common pitfalls like some soundness bugs we should be very careful about while using LLMs for this annotation generation task. And overall, we'll build on these strategies to come up with an inference type agentic framework, DafnyPro, which both improves performance and the correctness over the prior works. And as we can see, like we can use this DafnyPro, this inference type frameworks, and like frontier models to actually curate data sets, which can be subsequently used to improve like the performance of the smaller LLMs by fine tuning. So, but yeah, in this talk, I'll be mostly focusing on like the inference time framework, and I will refer the audience to check the fine tuning results from the paper. Now, what is like the primary strategy that has been utilized in the prior works is to generate multiple attempts through the LLMs with annotated code iteratively, and try to verify those annotated code with the Dafny verifier. If the annotated code succeeds, we stop there. Otherwise, you use like the Dafny error message as feedback to guide LLM to generate the next annotated code. So how this works? So this is like the first attempt generated by the LLM, which doesn't actually get proved because like the invariance it predicts is not actually inductive. But if you pass it to the Dafny verifier, this is like the error message. Now, if you feed this error message back to the LLM and regenerate again, the LLM now provides a inductive invariance, and that was actually able to prove the correctness of the program with respect to the pre and post condition. Now, one key details I have skipped is like how these annotations are generated. The common techniques that are used in the prior works is to regenerate the entire code with these annotations. This is done because it can be like there can be nested loops, and you need to insert assertion statements to guide the Dafny verifier at different program locations. So it's easier to regenerate the entire code with annotations. However, this comes with one concern that sometimes like the frontier models actually cheat and essentially modifies the base code logic to essentially push the proof over the line. And some of the prior works actually have this problem. They had used some basic string-based ad hoc techniques to check whether the base code is getting modified or not, but there are always these corner cases that has been missed. So blindly trusting like the LLM to regenerate the entire annotated code again can be risky. This is where our first contribution is, like we to formally check whether like the annotated code modifies the base code logic or not. We take both the base code and the annotated code, pass it to Dafny verifier, and check whether the added programming blocks can be exactly parsed as annotations like invariants, ranking functions, or assertion statements. If not, we return the error message, and if only the merge is successful, then we move to the next step, which is calling the Dafny verifier. So with this gives out the first attempt we took. So essentially, given a base code, we generate the annotated code with the LLM and pass it to the code merger. If it fails, we return the error message and retry again. And if the merging successful, only then we move to the Dafny verifier. And if it is verified, we stop there. Otherwise, we retry again with the error message. Now we'll be I'll be reviewing like both the successful attempts and like the failure cases to further improve the pipeline. So if you can see this program, so actually like the frontier LLMs like Claude is actually quite good in finding this invariance. For the example, it could find like the correct inductive invariance that prove the correctness of this selection sort program, which has multiple nested loop. Now, where actually things are failing. So, for example, if you look at this case, we found out like the LLM generated invariants are actually quite close to proving the property, but it was actually not quite there. So it was actually missing some small bits of information that could push the proof over the line. For example, if we look at with this set of invariants, what we couldn't actually prove like the post condition, but what we could prove that this property, which is quite similar to the post condition, but not quite there. But if we look at like the ground truth of this attempt, like what was missing was this additional assertion statement about the array slicing, which essentially pushes the proof over the line. So this assertion statement, like the LLM couldn't figure out, and if you don't provide this hints, actually like the LLM based search gets derailed and it tries to add some invariance that is not inductive, and essentially over the 10 attempts it couldn't get the proof over the line. And one good thing about this problem is like if you look at like the assertion statement, it was not really specific to the problem itself. It is more like a property of array slicing. So what we can do, we can build a data set of this type of hints which are problem independent and use this data set during this generation. So we can call this data set with the context like the previous attempts and the error messages and retrieve relevant hint from this data set, and which actually guides the LLM generation in the subsequent attempts. So this is what we call hint augmented generation. So now the question is like how actually we retrieve these hints. So we can actually use an LLM itself, like which essentially, given the context or all the failure attempts and the error messages, it calls like the retrieves relevant hints from the data set. And the second question is how we can like build this set of hints automatically. So for this, we also use LLMs. Like given a wrong attempt and the ground truth problem, we can actually use the LLM to find what was like the missing bits here. So for example, like the example I shown in the previous slide, it actually figures out like what should be the missing link so that the proofs can go over the line. The next issue we figure out is like the frontier models are quite verbose. That means like it adds way more invariant clauses that is actually required. So one of them is not proved to be inductive, then the entire proof fails. But what we observed, like if we just ignore that specific invariant clause, with the rest of the invariants it can actually prove the property. So the best simple solution is just to prune out those additional invariants and try to prove the output specification with the rest of the invariants. That becomes our second strategy. So what we do in this case, like in the inference-time framework, if you get an annotated code which is unverified, so with some invariant clauses that are not proved to be inductive, we greedily prune out those invariant clauses that are not proven to be inductive and try to prove the post condition with the rest of the invariants. So now how we decide which invariants to be pruned? We just greedily decide on pruning all the invariance clauses that are not proved to be inductive. Now with this, we arrive at our inference-time agentic frameworks, which builds on like the first attempts with this 2 additional component, which is like the hint augmentation that retrieves relevant hints for the context, and the invariant prover, which try to detect whether there is some invariance that is unnecessary and which is not proven to be inductive, and prune those out and try with the rest of the invariant clauses. Now we evaluated our DafnyPro framework on these 4 data sets, in which like the Dafny, which is like the largest data set we have. So for all all of these benchmarks, we evaluated like what is the percentage of programs that are verified by the DafnyPro framework, and for each of this problem, we gave LLM multiple attempts, which consists of 3 different steps, which is like prediction, which is like the annotated code generation, pruning, like removing some invariants that are not needed, and the hint retrieval step. So this is like the results on like the Dafny. So on different benchmarks with like the Claude 3.5 and Claude 3.7 model. So in blue we showed like the first attempt results, which didn't use like the hint augmentation and the pruning step, and we show like we significantly improve on with DafnyPro with those 2 additional steps. Now these are the numbers. So with DafnyBench, which is like the largest available benchmarks, which actually go near 86% of the problems to be verified by Claude 3.5. Now if we look at the breakdown of the improvement, so if we see like the hint augmented generation results in like the highest jump in the number of percentage of verified programs. And now one important observation is like we found like some of the programs used in the DafnyBench was actually faulty, so we fixed those examples with essentially the rewriter we use for the deep merging strategy, and that also improved the performance by 3 to 4%. Now I will be actually going over some specific examples where like the hint augmented generation is actually improves performance. So this was like the example which motivated this hint augmented generation, and if you see with DafnyPro, actually the LLMs figures out the correct hint. And not only that, given like the hint is actually not dependent on the very specific problem, is like more dependent on the array slicing property, is actually generalized for other problems as well. For example, this is another case where explicitly adding the same assertion statements pushes the proof over the line. So yeah, with that, I will conclude my talk with 4 more representative slides from the presentations. So first, we described about the cheating examples and how to prevent like how to ensure like the soundness of the LLM based annotation generation of the Dafny programs. Second, we discussed about like the hint augmentation strategies and show that it can be very useful technique to improve the performance of the verified program like annotation generation. Like then we discussed like the overthinking problem and like the pruning strategy, and then like the DafnyPro agentic framework that's essentially combines all the components and gets very good results on like existing benchmarks like DafnyBench.
Any questions?
And if the next speaker can come.
So this is more of a remark than a question. So this work was done this year?
Yes.
Or last, okay. So,
it's 2025.
So it must have helped the frontier